Today we're going to talk about the neuron, okay? It's also why I yell for the video. I yell very loud. Okay, so today we're going to talk about neurons, and we're going to start by drawing a picture of a neuron. So a neuron is a nerve cell, and they're found in the brain and the spinal cord, which is called the central nervous system, as well as down from the spinal cord out to the body, and from the body up to the spinal cord and eventually up to the brain, right? So we start with the neuron. It has three basic parts. This is going to be my rendition of a neuron. Okay? So the first part is this part here, and it's called a dendrite. And a dendrite receives information from other neurons. The second part of the neuron is the cell body. This has the nucleus and so forth and keeps the neuron alive. This extension out here is called it's the third part, and it's called the axon. The axon's job is to send information to other neurons. And the very ends of the axon are called axon terminals. Terminal is another word for end. Okay? So the direction, the flow of information through the neuron goes in this direction, from the dendrite through the cell body, through the axon to the axon terminals. And the process that neurons use to communicate with each other, and also the actual communication process and the flow of information, is an electrochemical process. An electrochemical process. Okay, the electrical part is what happens within the neuron. So within the neuron, the process is electrical. Between the neurons, the process is chemical. So notice that I put chemical in green and electrical in blue. So each neuron is connected at its dendrites and axon terminals to hundreds of other neurons. And the way that they're connected is that always, sorry, I got the wrong color here. Where's my black? Okay, so the axon terminals of one neuron are going to be connected to the dendrites of another. So let's say this little neuron here is neuron 1. The axon terminal of this neuron is going to meet with the dendrite of this neuron, which we'll call neuron 2, the big one. Where they come together, that area is called a synapse. So a synapse is the space between the neurons where the neurons communicate with each other. And the way they communicate with each other is through chemicals. These chemicals are called neurotransmitters. So in green here, the chemicals are called neurotransmitters. These are chemicals that neurons use to communicate. And they control everything about us. Our thinking, our language, our dreaming, our sleeping, our eating, our movement, everything, okay? So every neuron is connected at its dendrites to hundreds of other neurons, specifically to the axon terminal of one neuron, which comes together to meet the dendrite of another neuron in a place called a synapse. And in that synapse, the neurons communicate via a chemical called neurotransmitters. So far, so good? Okay. So we were talking about how the axon terminal of one neuron is meeting with the dendrite of the other. And the way the communication takes place, it's a chemical communication, and the direction is from the axon terminal of one neuron to the dendrite of the other. Okay? From the axon terminal of one to the dendrite of the other. But this big neuron, and all neurons, also are connected to hundreds of other neurons at their axon terminals. So the axon terminal of this neuron is going to meet with the dendrite of hundreds of other neurons. So this, again, where an axon terminal meets a dendrite, is once again a synapse. So every time an axon terminal meets with a dendrite, it's called a synapse. And the order of information remains axon terminal to dendrite, right? So in every situation, the axon terminal of one neuron sends information to the dendrite of the other neuron, and that dendrite receives the information. Okay? So far, so good? Okay, so now I'm going to tell you that every neuron has what we call a threshold of sensitivity. Okay? So I'm going to draw a chart or a graph or whatever the heck this is, a graph, and I'm going to show you, here's the neuron's threshold of sensitivity. And at its dendrites, at the dendrite, the neuron is tallying up how much neurotransmitter it's getting from all of its synapses. All of its dendrites are getting how much neurotransmitter, okay? So this is the amount of neurotransmitter on this axis, the vertical axis. This is the amount of neurotransmitter that the neuron is getting, and this second, the horizontal is basically time. All right, so what is going on is that this neuron at its dendrites is picking up on this chemical. We're back to using green because it's the neurotransmitters being represented by green here. So it's picking up on how much am I getting, how much am I getting, how much am I getting. And when it reaches its threshold, the neuron will fire, okay? So an electrical impulse will flow through the neuron. When the neuron reaches its own particular threshold, every neuron has their own threshold, basically, okay? And so when it reaches that level, it will decide to pass a message, and it does that by having an electrical impulse. So notice I'm using blue, because within the neuron, an electrical impulse will flow through the neuron and culminate out here in the neuron, releasing neurotransmitter molecules at its axon terminals. So let's get some terminology first, and then we'll talk about that again. When a neuron does not fire because it has not reached its threshold, this is called a resting potential. So as long as it's below threshold, the neuron does not fire, meaning it does not pass a message to other neurons. Okay? It just sits there. Okay? And so that resting potential means it's not firing or not passing a message. On the other hand, when the neuron does reach threshold, the electrical impulse flows through the neuron, which is called an action potential. An action potential means that the neuron fires, in other words, that it passes a message along. And how it does that is by releasing neurotransmitter molecules at its axon terminals. And the hundreds of neurons that it's connected to at their dendrites will pick up on this chemical and determine what it wants to do, what they want to do. So every neuron has one option and one option only. Its option is to sit there and remain without passing a message, which is called just staying in a resting potential, or if it reaches threshold, it will fire, which means it has an action potential, and it will pass the message. It passes the message by releasing neurotransmitters at its axon terminals. So each one of these neurons does that. So neuron 1, this little one that we saw over here, okay, neuron 1 tallied up how much neurotransmitter it was getting at its dendrites and determined that it reached threshold. So an electrical impulse went through that neuron and culminated in that neuron 1 releasing these neurotransmitter molecules into the dendrites of all the neurons that it's connected to. And neuron 2 is not just connected to neuron 1, but to many other neurons. At its dendrites, it's tallying up, am I getting enough neurotransmitter molecule to reach my threshold? If it does reach its threshold, then what will happen is that it too will fire. In other words, it will have an action potential, meaning an electrical impulse will fire through the neuron, and at the end of its axon terminals, it will release neurotransmitter molecule. And the hundreds of neurons that it's connected to, okay, all the dendrites of the neurons it's connected to, will do the same thing. They will pick up on that neurotransmitter molecule and determine if it reaches their particular threshold, each of theirs, and some may fire because it reaches their threshold, and some may not, because it does not. You with me? Okay. Now, you see up here on the first slide, you see that you have this picture of a neuron. It's really hard to see, but these are the dendrites that receive information from other neurons. This is the cell body. It has the nucleus, as you can tell, and many other things. And then you have the axon, the sending part. The axons can be very long. They can be as long as we are tall, but it doesn't mean you have an axon from the top of your head to the bottom of your feet. It means they're very convoluted and they can be very long, okay? And then the ends of the axon, which are the axon terminals. But something you're not seeing in my picture over here is this golden stuff. You see that golden stuff right there? This stuff is a fatty substance called myelin. Sometimes you hear it called myelin sheath because sheath is just another word for covering, okay? So this is a fatty substance that grows along the axon, and it leaves these little spaces in between the little fatty growths. So it's like donuts on a stick with a little space between each donut. And what's going to happen is that this fatty stuff does not conduct electricity well. Now remember, the signal within the neuron is electrical, right? So this electrical impulse, when it gets to these myelinated sections, rather than go through every little piece of the axon, it's going to actually jump the myelinated sections and go from what we call a node of Ranvier to another node of Ranvier. Okay, now you don't need to know that term, but I like to say it. It's a cool word. So anyway, these little spaces in between are unmyelinated, and the electrical impulse will jump these sections, okay, that are myelinated, and when they get to the axon that is still uncovered, that node of Ranvier, they will jump to the next one and to the next one. This makes the transmission, the electrical transmission, faster and smoother, okay? So let's say one of my markers here is the axon. The electrical impulse would have to flow through the entire axon, meaning it's going to meet the resistance of whatever it's made of. In this case, plastic and probably velvet inside and some liquid ink, right? So instead of doing that, I can put a rubber band around the axon, around the marker, and leave just a little space in between a bunch of little rubber bands. When the electrical impulse flows through the marker, the electrical impulse will actually jump the rubber areas, the areas that are covered with the rubber band, and that will make it faster and smoother. So when we're born, we're not nearly completely myelinated. In fact, you know that little kids like in kindergarten and preschool, they don't use a regular size Crayola, do they? Right? They use the big fat ones, right? Everybody know that? Okay, you're looking at me like I'm weird. Okay, so they don't have the control over their muscles to try to grab something so small. This is a fine motor skill, okay? That's what they call that, as opposed to gross motor, which means like big muscles, okay? So they give them big ones, and they're probably not going to hold it that way either, right? Because that's too advanced. So they might hold it like that, or something, you know, or like this, or something like that, but they don't have control over that, in part because they're not completely myelinated yet. So myelin allows us to have the precision and control because things can move faster and smoother. The last area of the brain to myelinate is the area of the neurons in the brain to myelinate is the area that controls our ability to pay attention. So even into your teenage years, that's the last thing to kind of come together. All right? Now, you guys, I'm sure have heard of muscular sclerosis, right? MS. And people who have MS, they're shaky, and they may fall, and they can't do things very well. Eventually, it affects their speech as well, because they have to, you know, we have to control the muscles of our tongue and our pharynx and all of that stuff to be able to speak, our lips and all of that, okay? And then eventually maybe they are bound to a wheelchair because they can't walk. Well, one of the problems going on in MS is that the myelin starts to just fall out. It just starts to deteriorate, is the word I'm looking for. And so it's not there anymore. And the worse it gets, the harder it is to do things smoother. Okay, so let's look at a couple of other slides. The second slide shows you a magnified picture of neurons, 500 times magnified. Okay? Now, it's easy to see where the cell bodies are, right? And you can see the nucleus in there and stuff. But the rest of it looks like a hot mess, right? And I want you to know that the neuron that we're talking about that's so simple with dendrite, cell body, axon, is only one kind of neuron. And when you're in school, this is the only one they teach you about. But in reality, there are neurons that have like 2 sets of axons, and I mean, it gets complicated, okay? I also want you to notice these little purple cells here. The little purple cells are called glial cells. So let me take you there for a minute. Glial cells are called that because glial is a word that means glue, and that is what the glial cells do, is they kind of hold the nervous system together. So they're much smaller than neurons, and they outnumber them about 9 to 1. During prenatal development, the glial cells actually are very important to the formation of the nervous system. And they also then provide some housekeeping kind of functions for the neuron. But that you should also know, and the reason I'm bringing them up now, is that they're really important to the development of the myelin sheath, the covering. So they literally reach out and cover the axon with myelin, okay? So, while we're here, we might as well talk about the three kinds of neurons. So one kind of neuron that you have is the sensory neuron. These are neurons that come up from your sense organs up to your spinal cord, and then of course eventually to your brain. So they come from your skin and your eyes and your nose and your ears and all of that. Okay? And then there are motor neurons. And motor neurons go down from the brain and spinal cord. Then you get, the message goes from the brain through the spinal cord and then down to your muscles and glands, because your brain wants them to do something, right? Put out this hormone or move your arm or something like that. And then we have what we call association neurons. And association neurons are basically in the central nervous system, in the brain and the spinal cord, and they communicate with each other. So now that you've seen this firing of the neurons, you need to know that physically, this is all we boil down to. Your thoughts, your feelings, your aspirations, your behaviors, your appetite, your sleepiness, everything boils down to your neurons firing. And what I want to do now is I want to take you to one of these synapses, and I want to kind of blow up the synapse, right, and get real into it and see what happens there. So I'm going to bring you here, and we're going to talk about a synapse. So on this side of the board, I'm going to draw two neurons coming together. And this will be a synapse. Now when we talk about a synapse, we mean the axon terminal of one neuron, the space between the neurons, and then the dendrite of the receiving neuron. Okay? So I'm gonna draw a picture of a neuron, of a synapse, and I want you to tell me what part of neuron 1 is this. If neuron 1 is sending information to neuron 2, then what part of neuron 1 is this? The axon terminal. And what part of neuron 2 is this?
Dendrite.
The dendrite. Okay. So what's happening in there? Now, I actually forgot to do something that I normally do. So I'm going to do it real quick, and then I'll get back to this. So what I need are about 4 volunteers who are willing to come up here and stand with their arms out. You're not going to say anything, you're not going to do anything. I just need you to do this. 4 people, come on up. Thank you. Don't be shy. You're just going to stand up here with your arms out. 2 more people, come on. Thank you. 1 more person. Volunteers can also be voluntold. Okay, guys, so you're going to spread your arms out and not touch. So scoot over a little bit. All right, what do we got? 1 more person, come on. Calvin, are you? One of you get out there. It doesn't matter if there's 5 of them home. Okay, scoot over this way. Everybody go. Everybody scooch. Okay. All right, so each one of these people is going to be a neuron. Now, this is a silly thing, but in 28 years of teaching, somehow this works. Now, you guys seem to be getting it really well, but other classes have trouble, and this always helps. So we're going to do it anyway, okay? So each one of these guys is a neuron. Remind me of your names. Josh. What? Malcolm? Okay. Griffin? Frank? I'm never going to remember your names. You'll have weird names. Josh, okay. So this is Josh's dendrites over here, okay? And this is his cell body in his axon. And then there's a synapse, a space between him and Malcolm, right? And
Griffin.
I knew that a minute ago. Okay, and Frank. Okay. So that's how this is going to go. All right, so at his dendrites, Josh is connected to hundreds of other neurons. And he has a certain threshold. Okay? It can be a higher or a lower threshold. And if he picks up on enough neurotransmitter to get to that threshold, an electrical impulse, he will have an action potential, which means that an electrical impulse will flow through him, through his cell body, down his axon, skipping the myelinated sections, right? And it will culminate in him at his axon terminals releasing neurotransmitter molecules. And then, just a minute, Malcolm is going to decide for himself whether he should have an action potential or not. So he's picking up on the neurotransmitter that he just got from Josh and all the other neurons that he's connected to, and he will determine if he should fire. So if it's enough to reach threshold, he will have an action potential, which means an electrical impulse will flow through him, flow down his axon, skipping the myelinated sections, okay? And he will release neurotransmitter molecules into the synapse, the space between his axon terminals and Griffin's dendrites, right? Now, Griffin is receiving the information not just from Malcolm, but from hundreds of others, right? And so he might determine it's not enough. He might have a really high threshold, and it's not enough. So Griffin decides not to fire. He remains in a resting potential, okay? Which means that Frank would never get the message, right? You get me? Because Griffin stopped the message. You got it? Okay, thanks guys. Thanks for not complaining about holding your arms up. Every class is like, oh my God. It's like, you guys are supposedly, you work out and all this shit. You can't get up here and hold your arms out there. All right. Okay, so let's talk about that synapse. All right, so the axon terminal of one neuron is going to come together with the dendrite of another. So remember that this one has its threshold, and if the chemical got up to its threshold, it fires, right? Which means an electrical impulse went through it, and now I'm going to show you what happens at the axon terminal. So first, before we even talk about that, every person has to make neurotransmitter molecules. That's my factory that makes neurotransmitter, okay? And so that we have to do that, and then at our axon terminals, we store these molecules of neurotransmitter in these bubbles called synaptic vesicles, which you don't really need to know. But inside the vesicles are these molecules of neurotransmitter. You know what a molecule is, right? Smallest thing you can have to atoms and shit that you can have to have that particular chemical. So for example, water is 2 hydrogen and 1 oxygen. We have just now reached the pinnacle of and the complete story of my understanding of chemistry, okay? So two hydrogen and 1 oxygen, right? So that is a molecule of water. All right. So this is a neurotransmitter, and its molecules are there. So what happens? Yeah. Okay. What happens when the electrical impulse reaches the axon terminal? Here's what happens. It's called release. Okay, and the molecules are released. So while they're in this bubble, the molecules don't fit through the cell wall. But when there's an action potential, the vesicles, the synaptic vesicles, come out here to the cell wall, and then they bust the bubble. You know, like when you blow a bubble and it touches something, it might bust, right? Okay, so it busts the bubble. And the molecules inside that bubble now do fit through the cell wall. You got it? Okay, so out come these molecules. So this is the release of the molecule into what we call the synaptic gap or cleft. So this entire thing is the synapse. Axon terminal, space between them, and the dendrite. The space between them is called a synaptic gap or cleft. The synaptic gap or cleft. Okay? And that's the actual space between the neurons. So during the first step of an action potential, after the electrical impulse reaches the axon terminal, the vesicles will pop and release the neurotransmitter molecules out here into the synaptic gap or cleft. Okay? Now the receiving neuron, all neurons at their dendrites have these little things called receptor sites. So, what color do I want to use? Okay. So these little receptor sites are like a special little lock, and the molecule fits perfectly into that receptor site. So let's say that the molecule is shaped, I'm going to make my own life hard right now. Sorry, shut the finger right on camera too. Okay, let's say the molecule is shaped like that. Okay? The receptor site would be shaped exactly to fit that molecule. So the receptor site would be shaped like that. Wow, I really suck at drawing. Okay. You with me? So this is the neurotransmitter molecule, and here is the receptor site. Okay, so this is a receptor site. So on your test and on the final, they may ask you, how does this work? And it works like the neurotransmitter is the key, the molecule is the key, and the receptor site is the lock. And that key specifically fits that lock, okay? So the neurons have receptor sites for one type of neurotransmitter like dopamine, and another for serotonin, and there's actually receptor sites for various types of serotonin and so forth. So the first step is release, and now the second step is binding. These little molecules are going to be attracted to these little receptor sites. And so they will come in and they will bind to these receptor sites. Okay? So the first step, sorry, I went ahead here. All right, so the first step is release. The second step is binding. The molecules actually hit the receptor site. What does that mean? Okay, doggone it. All right, so here is this neurotransmitter threshold. This is a dendrite. And here, it is picking up on how much molecule it's getting. So, every time that one of these little molecules hits a receptor site, it's a go message. I'll put a plus on there, okay? So, every time that one of these hits, it makes it go closer and closer and closer and closer and closer to threshold. You got it? Every time that one of these molecules hits the receptor site, it's telling it, you got more neurotransmitter, you got more neurotransmitter. You with me? Until it possibly could get to threshold. But here's the deal. Binding is not just it goes there and it sits there. They bounce in and out of the receptor site. So this molecule could bounce out. It bounced in and it gave it the message, and then now that one bounces out and it's hanging out over here, and this one comes in and bounces in. There's another message. Every time there's a bounce in or out, it's another message getting in closer to you have more neurotransmitter. Okay? Or this one might bounce out and then bounce right back in, okay? So there's another message. So we're getting closer to that threshold. So each bounce gets us closer and closer and closer to the threshold. You got that? Yeah? Eyeballs. Look at me. Do you understand what I'm saying? Everybody good? Okay. So the neuron has an action potential. An electrical impulse flows through the neuron. It releases neurotransmitter molecules into the synaptic gap or cleft, and those molecules then bind to a receptor site, not just once perhaps, but they bounce in and out. And every time it hits a receptor site, this receiving neuron thinks, I got more neurotransmitters, so maybe I should fire. Okay? Now the next thing we're going to do is we're going to talk about how do we inactivate or clear it out. In other words, how do we stop the action potential and get ready to know if we should fire again? Okay, so inactivation means that we've got this activity of them bouncing in and out. Now we got to stop so that if this one wants to send another message, we can be ready for the second message. You with me? So let me tell you how this happens. One way that it happens is that sometimes these neurotransmitter molecules just float out of the synaptic gap. They just float on out and go bye-bye, okay? That process is called diffusion. You don't need to know that, but some of these will just float out of the area, and therefore, if they're floating out of the area, they will no longer be available to hit these receptor sites. You with me? Okay, another thing that happens is that we have enzymes, we have enzymes that live here in the synaptic gap. So these have left the building. Okay, let's knock these out. All right, so these enzymes, they break down the neurotransmitter molecules. They break them down, meaning that they break them into parts. So in my fabulous example of water, they break it down into 2 hydrogen and 1 oxygen. So it's no longer water, right? There's hydrogen hanging out over here and oxygen hanging out over there. You with me? How many times? Do y'all like to see my butt? Because apparently I really like to bend over. One time when I was younger, I said something like that, and this girl threw her pin way over here, so I'd have to bend down again. But that doesn't happen to this guy anymore. Just saying. But there was a day, that one day, it was just a Tuesday. Okay, so you with me? The enzymes break it down. So here's what happens. Let's say we break this molecule in 2. So if you have one piece of molecule that looks like that, and this other piece is rolling around over here somewhere. Oh man, I can't even draw that. Okay, you with me? Then can one of these make this receptor site happen? No. A half of a key is not going to turn a lock, right? So when you break it down, it might try to go in there, but it's just going to bounce right out without doing anything. Okay? So we're breaking those down. Then we have this other thing over here in the sending neuron. In other words, at the axon terminals of every neuron, we have reuptake centers. And a reuptake center is a recycling center. So what those centers do is they take up whole molecules, entire large molecules, complete molecules of this neurotransmitter, as well as these little parts that were left over, and they recycle them. So they take up a bunch of this stuff and recycle it. You with me? So now between some floating away, some getting broken down into parts, and the parts and the wholes being taken, I guess we should say, I don't know if we're going to say that, then we've basically cleared out this synapse, the synaptic gap. You with me? Now, this one is ready to receive a message again. So notice that whenever I draw this electrical impulse, I draw it, it goes up, and then it goes way down, right? And that's because for a split second, and I mean a split second, okay, the neuron can't take a message, okay? It's like, I just got a message, I just fired, give me a second to clean everything up, and then you can send me another message, okay? Everybody got it? All right. Let's talk about why all this junk is important. We're going to talk about it at length next time, but I just want to give you an idea. Okay, so the body has to make the right amount of neurotransmitter. It's possible for you to make too much or too little of a neurotransmitter. If you make too much of a neurotransmitter, you might have too much of that rolling around. If you make too little, then you're not going to have enough of that neurotransmitter active in your body, right? Yes? Okay. Then you have these receptor sites. The receptor sites have to be present, open, and be in the right number. So some people have too many receptor sites. For example, we think that people with schizophrenia have too many receptor sites for dopamine, okay? Some people don't have enough receptor sites. So people who use the street drug ecstasy, they permanently kill off their serotonin receptor sites, okay? They also have to be unblocked, because you can give medications or take street drugs that act like the neurotransmitter or block the receptor site. You can have something that will get in here, it's not the neurotransmitter, but it fits, and it just stays there and doesn't allow the real molecule to get in. So you're blocking that receptor site. Other times, you can have something that's not the neurotransmitter, but it fits here. So it fits, but it's different. But it's close enough that the receptor site thinks, I just got that neurotransmitter, right? You got it? Okay. Those enzymes, we can block the enzymes too. If we block the enzymes, then what we're doing is making more of this available, right? So if we're not breaking it down, there will be more whole neurotransmitter molecules that can fit into the receptor sites. And then we can also block the reuptake so that we don't take back those molecules, and they're more likely to actually reach their receptor destination. Okay? So let me ask you some questions. If you have too many receptor sites, will you have more of that neurotransmitter's activity or less?
More.
If you have too few receptor sites, will that lead to more or less activity of that neurotransmitter? Less. If we block the enzymes from working, will that lead to more neurotransmitter activity or less? What? If we block the enzymes? It would be more, because we're blocking the enzymes which break down the neurotransmitter. So if I don't break it down, then I have more of them to continue to bounce in and out before they fall apart into pieces, right? Before they're broken down. If I block the reuptake centers, will I have more, like for example, if I block these reuptake centers, will this neuron fire more or less?
More.
More, because I've allowed more of these to stick around and come and find their way into these receptor sites. So this one is likely to fire more. You with me? Okay, so we're going to talk about specific cases of that with different disorders and things like that, and what's happening in each. Okay, the next thing we need to talk about is called the all or none law. Neurons have one option and one option only, to fire or not fire, okay? So when a neuron fires, it fires at full speed and full intensity. So a neuron is like the light switch, right? I can either fire and turn the lights on, or not fire and keep them off, or turn them off, or whatever. I don't have a dimmer. It's not like a volume switch. The neuron can't fire more intensely or less intensely, okay? It can only fire or not fire. When it fires, it does so at full speed and intensity every time. So it's either on or off, that's it. So having said that, then you might think, well, what is it that makes a difference then between a gentle stimulus and a stronger stimulus? So weaker or stronger. How do I know that that sound is soft versus that sound is very loud? How do I know that the light is dim versus bright? How do I know that that's a paper cut versus my arm just got cut off? How do you think that is?
Is it the shape of the neurotransmitter?
No. Okay, so the difference is that the stronger the signal, the more neurons are firing. Okay? They also fire over and over and over again. Make sure you know that, okay? The stronger the signal means more neurons are firing. So let me show you that. This has to do with the neuron's threshold. Some neurons have very small or low, I should say, thresholds. A low threshold means that the neuron requires very little stimulation before it fires. And a large, or I should say high threshold, means that it needs much more to fire. So, there are neurons whose threshold is very small, very low, okay? And when it's a very low threshold, this neuron, if it gets just there, it will fire. And this might be a very dim light. Or if we're talking about sound, it might be a very low or gentle sound, a very, what am I call, soft is the word I'm looking for. A very soft sound. And then you go up. Neurons have higher and higher thresholds. So many neurons have higher and higher thresholds. And what's going to happen is that when there's a very loud noise, so let's say this is a loud noise, all of the neurons, these neurons that have that high of a threshold are firing. But since the noise was way up here, all of these are also firing at the same time. Does that make sense? So a neuron that needs this much stimulation to fire is going to mean that all of the ones that needed less stimulation, they already got there, right? They already fired. You with me? So let's say you're looking at how much stimulation are you getting, okay? And you get to here. Well, if this one is firing right now, obviously this one reached threshold, and that one reached threshold, and that one reached it, right? So now they're all firing. You see what I mean? They fire whenever they reach threshold. Okay? So each one fires when it reaches its own threshold. So by the time you get to a high threshold, all the other ones you already got there and passed it, right? You got there and you went past it. So there are neurons that fire when a fly lands on your arm. They require such a tiny, tiny bit of pressure for you to notice, right? So if I don't know, a piano fell on my arm, the neurons that normally fire when a fly is on there, they're all firing. And so are the ones that would fire if a book fell on my arm, or if a, whatever, the desk fell on my arm, or, a tire fell on my arm, all the way up. You see what I mean? So how do you know that you got a paper cut versus how you know you cut your arm off is, when you cut your arm off, there are neurons firing that have never probably fired before, because they require such an amount of pressure or pain, okay, at such a deep level.
So the level of pain, or in this case, a stimulus, it's what stimulates the neurotransmitters on the neurons, right?
Yes, some neurons respond to pain, some neurons respond to light, and some neurons respond to just, to their association neurons, so they're just about thinking or things like that. I mean, it gets very complicated.
And those cells that gets activated when there's a really high pressure or pain, like the ones you said, they've never been activated before, the ones that have a really high threshold, they need that big of a pain to be
Right.
activated, like a piano falling or your
Right.
arm.
So you might live your whole life and those never, if you don't cut your arm off, let's say none of us in here, then there's a level of firing that some of those neurons are going to spend their whole life going, I'm waiting for that damn piano, okay? And they ain't going to fire because it ain't coming. So hopefully, right? Okay? Does that make sense?
So, if I only do this, I
Right.
mean, some of them are already firing.
Some of them are firing.
I mean, because there's
But
a
the
simple
ones that-
touch.
but
But
you
if
don't-
I stop myself,
Don't do it.
No.
But yes, if you did stab yourself, those would fire because it's already there, right? But so would others that require more stimulation to get to fire. So how you know the difference between a gentle versus a harsher stimulus is that more neurons are firing, okay? More neurons are firing. And they also tend to fire like over and over and over and over, rather than just fire and fire. They're like, damn it, damn it, damn it, damn it, damn it, when your arm's cutting off. Yeah?
So have you heard of those people who don't feel pain? Is that because they don't have the...
It's not that, it's other things, because pain is a very complex thing, okay? We feel pain at various different levels. And so there are people who don't feel pain at a level of these, just skin and stuff like that. And there's people who don't feel pain at the level of their processing. Where you, like for example, like people who can do certain things and withstand certain amounts of pain, it's not because they can't feel or their neurons aren't firing. It's because up here, their association neurons are blocking that signal from getting to their conscious awareness, which is the highest level of the brain, which we'll talk about, okay? But, but not feeling pain is a bad thing. It's a disorder, because these people, they hurt themselves badly and they don't realize that they've hurt themselves, and they can really ruin them physically. So it's not, most of us think, oh yeah, that'd be great. It's not really, okay? We all need, pain is a signal, right? Stop that. You're walking on that foot and it hurts. They're like, stop that shit, stop walking on that foot. Get your hand out of there, it hurts, whatever.
Actually, this is why some athletes who have been doped during competition, they've died in the middle of a competition, because when they dope themselves, when they get drugged, and they don't feel the pain or the soreness of the extra effort they're making, because they just want to get to the goal without feeling any pain, and they're like, oh yeah, I'm doing great without feeling pain, and suddenly they fall and then they die. That's happening.
Bad idea.
That's
Don't
what's
fall and
happening,
die.
and that's why it is very risky to drug in order to enhance performance, because that's the risk it comes in.
Okay, next time we'll finish up on this presentation, okay? And then we'll go to the next one. Thank you.